Now let's look at multiple polylogarithms. Which we abbreviate as MPLs. So they are defined as iterated integrals, denoted by G, with some number n plus 1 of complex arguments, where the last one is the last endpoint of integration. You have some integrand with a linear denominator, and then they're defined recursively in terms of the MPLs with smaller numbers of arguments. And these are iterated integrals of some definite weight, which is transcendental weight. And the starting point here is g of z equals 1. And we also define g of any number of zeros followed by z, which would be a completely log divergent integral. And so we just define this to be 1 over n factorial log to the n of z. Now they can be given the structure of an algebra because you can, of course, add and multiply these functions, but what is particularly interesting, and I trust you've seen from Claude, is that when you multiply them, they respect a shuffle algebra, in terms of which a product of any two of these MPLs can be expressed just as a linear combination of MPLs whose weight is the sum of the weights of the two factors. So that is to say it's graded, a graded algebra, graded by weight. And it is also a bialgebra with a coproduct that I will introduce shortly. But to do that, instead, I will now give a second definition, which I'm not sure if you will have seen from the other lectures, which is to relax the lower integration endpoint, the value of the lower integration endpoint. So instead of integrating from 0 every time, we now integrate from any arbitrary a0. And just because these are both established definitions in the literature, you'll see that, so now we're integrating from a0 up to an plus 1. This is not called z in this notation. And also notably in the integrand, now we're taking the complex number in the denominator. We're not taking it from the beginning, but now we're taking it from the end. So this is an, and the arguments are going to come out in the reverse order. Okay, but this part of the iterated integral structure is the same. Our starting point, the original integration kernel seeding the iteration, is just taken to be 1. And so these are related to the g's above by an insertion of 0 for the lower integration point and the reversal of arguments, as I mentioned a moment ago. So we can easily convert g's to i's in this way. Now it's actually also possible to convert i's to g's systematically. Intuitively, you would integrate from your new base point, say up to 0, and then again from the other side, the upper endpoint back down to 0. It's not so trivial though, because this is going inside the iterative structure. So you do have to unwind the integration and then do that at the base step. But it is possible and to do this systematically, to convert any I into expression in terms of G's. Now we can define the coproduct if we assume that these arguments, the AI, are completely generic. Meaning they're not taking special values and don't have relations among them that could spoil this relations that I'm about to show. So that is the following, that delta of I with all its arguments is a sum of terms. And now we take a selection of indices. So we're going to be summing over values of the indices in between 0 and n. So this is I1 less than I2, strict inequalities here, ik plus 1. So we're choosing, in a way, some subset of indices. And we take those in the middle of the I here on the left side. It's I1 then, I2, ik, I0 and A0 and AN plus 1 are staying where they are. And then on the right side of the tensor product, we have a product P from 0 to K. And now we are going to pick up the A's that we might have skipped over here. And we pick them up sequentially in between each of these successive pairs. So it goes like this. So the P's, right, the P is from 0 to K, so it's going along with these indices here. So we start with AI sub P. Then we go from AI sub P plus 1 successively up to AI sub P plus 1 minus 1, and then AI sub P plus 1. So these are all, inside this factor, these are all consecutive A's, and they're all the consecutive A's in between I sub P and I sub P plus 1. This coproduct respects the grading. So what we have now is a graded bialgebra over Q, rational numbers. To see that this coproduct structure respects the grading, we just need to count up the arguments. So remember, the weight of the MPL given by G is n, so it's the number of arguments here minus 1. For I, it's the total number of arguments minus 2, or the number of arguments in the middle. So here, the weight is n of this MPL on the left-hand side. And here on the right-hand side, what's happening is we are conserving the number of these A's between A1 and AN. In fact, we're even conserving the values in each term, because here in each term we're just taking some subset, and then here what's between the semicolons are precisely all the AI's that were not between the semicolons here. And each of them will appear either on the left or in one of these factors on the right. So the total weight in each term is the same. There are nice pictures you can draw corresponding to this coproduct. I have a sort of polygon picture, so what you can do is draw say, a semicircle where at the corners you have a0 and an plus 1. Then you put all the other ai's around there equally spaced. And now what you draw is you draw some nested polygons that start and end at the end points. So here, what we're doing on the left is we're taking some selection of these points, and then we are connecting the dots with a polygon that begins and ends at a0 and an plus 1. And then in each of these factors on the right, then we're just filling in polygons as well, where you read off the arguments in between. So in between, in all these arcs, you just have to pick up any of the vertices, all of the vertices that were omitted in the first selection. And then reading each of these polygons, now with these new base points on the right side, as the arguments of an I, you recover the form of the coproduct. Let's specialize now to the case of weight 1. So for weight 1, we have precisely 3 dots, a0, a1, a2, and there are just 2 choices for the polygon, right? Either we include a1 in the polygon that will go on the left, or we don't. So let me draw pictures for these 2 terms. So in the first one, we will choose not to include a1. So our first polygon goes just like this. In the second one, we will. So then for the second level, now we have to include this vertex here in the entry on the right of the coproduct. And in this case, there's nothing else. These are just trivial on the right, so we get 1. So when we write out the coproduct, we get that delta of I, a0, a1, a2 equals, from this term, we have 1. Remember, that's the kernel of the iteration, where if there's no arguments in between, that's identically 1. And then the second one, we do have I of a0, a1, a2. And in the second term, the first one is the polygon, the iterated integral, and then on the right side of the tensor product we have just 1, only trivial contributions there. So this is the structure of all weight 1 MPLs. And weight 1 MPLs are all logarithms up to log identities. They're just plain logarithms, so we conclude that the coproduct of log of z is 1 tensor log z plus log z tensor 1. And from this, we can build up the coproduct of any product of logs, remember, because coproduct and product are compatible. So this is one way we start getting higher weight functions and their coproducts. So we have log x, log y. This would be the product of the coproducts. And so this is 1 tensor log x plus log x tensor 1. Same with x replaced by y here in the second factor. And remember, this kind of product of something that is a coproduct or in the tensor space just proceeds by taking products on the left and right. So here by binomial expansion we have 4 terms, And in each of those terms, we straightforwardly just multiply what's on the left and right of the tensor product. So we get 1 tensor log x log y plus log x tensor log y plus log y tensor log x plus log x log y tensor 1. We could also derive the coproduct of powers of logs from a direct application of the binomial theorem. We get the sum over k from 0 to n of n choose k log to the k x tensor log to the n minus k x. Now remember that if you propose a formula for the coproduct, that really the most non-trivial check, I mean, you have to check all the axioms, but the most non-trivial one is co-associativity. And here, again, similar to when we saw in the incidence algebra of the previous lecture, one can construct a formal proof, but I think we can convince ourselves just by looking at this picture of nested polygons. If you imagine taking an additional coproduct, either on the left, so on this inner polygon, or on all the outer polygons constructed on top of that, and then you get another nested sequence. And I think you can, and with a minute's reflection, realize that if you iterate the coproduct, then you get a triple tensor product, and each term will be represented by sort of triply nested polygons of this sort, where at each stage of the nesting, you're just going in between endpoints of the previous stage of the nesting. So we can, at least intuitively, declare we have checked co-associativity, and we understand it in terms of the nesting of polygons. Now, this really does have very much the same flavor of what we saw in the incidence algebra, and we can actually make that even more explicit. In a way, this coproduct is very much the same kind of operation as we had there. Because remember, in the incidence algebra, that was about taking subsets, and that's really what we are doing here. We have some set of arguments, and we're selecting subsets. And then we take sort of that over the original interval, or we build additional structures on top of each of those subsets. So another way of putting the coproduct on MPLs in these terms is we can write now in terms of the G's, the coproduct of G with some vector of arguments A and final argument Z is a sum over vectors B contained in A, where these B's are order preserving subsets, meaning the elements are given in the same order. So here on the left we have G of those arguments in B, with the final argument Z. On the right of the tensor product we have something new. So the arguments are the same that we had originally, but what is meant here by the by the subscript, is that we have a new integration contour. Right, so we see what's happening in the picture of the nested polygons is, in a way, we're picking different base points. So we can express this in terms of new integration contour that goes around, really circles around the singular points given by these arguments. These are singular in terms of that's where you find poles of the integrand. And when you integrate over this new integration contour, really what you're doing then is picking up residues at those poles. Again, this is only valid for generic arguments. And we're going to see this same kind of structure in Feynman integrals as well, where we define coproducts or coactions in terms of changing the integrand on the left and changing the integration contour in a very complementary way on the right. Now again, extremely important, this coproduct formula is valid only for generic arguments. An issue that arises with non-generic arguments is you can land on values where you have divergences. Now, divergences arise the most obviously if you're setting up a multiple polylogarithm, if you are integrating to the point of the last singularity. But what's a bit more subtle and extremely important about this coproduct formula is that even if you are taking the coproduct of a multiple polylog that is not divergent, by the time you apply this formula, or perhaps the more concrete version here, it could happen that some of these multiple polylogs appearing in the formula, that these are divergent even if the original one was not. So these can arise, so they're really unavoidable. We have to have a way of dealing with them. It can arise in the coproduct expansion even when the original I function is finite. So we need a regularization procedure, and we have one that's called shuffle regularization that we use. So we make use of the property of the shuffle product, use shuffle product relations to collect the divergences that appear, and it's true, though not obvious from what I've told you, that using shuffle product relations you can squeeze all the divergent parts, say, into multiple polylogs that are of this form G, where you have exactly all the same arguments. So then shuffle regularization is the prescription to do this, to perform such an algorithm. And once you have got these specifically divergent terms of this form, then just set those to 0. And one can prove that this is a consistent regularization procedure. Now we actually need to use shuffle regularization in order to derive the next concrete examples of coproducts of polylogs. So we've done it for logs and their products, and perhaps the next simplest functions are the ones called classical polylogs. And you've probably also seen these in Claude's lectures, but again, just to recap very briefly, they're called Li sub n, so there's one for each natural number n. They could be defined in terms of series, infinite series z to the k over k to the n. So note in particular that Li n evaluated at 1 is the value of the Riemann zeta function, zeta n. And okay, then we also have its representation as an iterated integral in terms of Li n minus 1 divided by t. And using that formula, we can express it in terms of the g functions we've defined above as g of some string of zeros and then 1 and then z, or in terms of the i's as minus I, 0, 1, as we're reversing the arguments, a string of zeros, and then z. So using shuffle regularization, I won't show it explicitly here, but it implies that we can compute then uniquely the regularized coproduct of Li n of z, and it turns out to be one tensor itself plus a sum of terms indexed by k going from 0 to n minus 1, Li n minus k of z tensor log to the k of z over k factorial. And in particular, if we take z equals 1, then we also derive the coproduct of the zeta values, coproduct of zeta n, just plugging it into this formula would be 1 tensor zeta n, and in this series, all the logs, the log of 1 is 0, so the only term that survives is the one with k equals 0, and that, evaluating it, gives zeta n tensor 1. Very simple. Now, if we consider this property more closely, we're going to arrive at a bit of a puzzle, which has everything to do with why we're going to need a coaction rather than a coproduct. So what we've been working with so far here really is a coproduct, but soon it's going to be lifted to a coaction, and it's motivated by considering zeta sub 2n, the even zeta values. Now, what's special about these is they are known exactly. They have an explicit expression in terms of Bernoulli numbers, and all we need to know here is that it's zeta 2n is some rational number times zeta 2 to the n. So Cn is just some rational number, which is well known, but we don't need it. And zeta 2 is pi squared over 6. So this is to say that zeta 2n is a rational number times pi to the 2n. And we can express it this way. So for example, zeta 4 is 1/15 times zeta 2 squared. Therefore, just by computing the coproduct according to what we had above, using the shuffle regularization and just this formula here, we would arrive at comparing it with the coproduct on zeta 2 squared, and this now is the square of its coproduct, so it's 1/15 times 1 tensor zeta 2 squared plus zeta 2 squared tensor 1 plus 2 zeta 2 tensor zeta 2. Now these two terms, these are the ones we want. These two terms reproduce this formula for n equals 4. This one is extra. So somehow we're going to want to set this to 0. So the resolution proposed by Francis Brown is to really define a coaction such that delta of zeta 2 is zeta 2 tensor 1 without the other term. So that is to say 1 tensor zeta 2, or really then anything tensor zeta 2, is 0. Claude Dürr then argued that perhaps we could even construct the coaction such that delta of pi would only be pi tensor 1, whereas if you compare to the formulas we had above, right, pi, or actually particular I pi, is log of -1, and you can construct exactly the same argument here by considering the square of e to the I pi, and when you take using the formula we derived for logs above, and you'd also argue that you do not want to see pi's in the second entry. And because log of -1 comes really with this factor of I, is why we often speak of taking the second entry of the coaction on multiple polylogs to be modulo I pi. So it's in this sense that the two entries here in the coproduct, the left and the right, are in different spaces. On the right, we're working modulo I pi. On the left, we're not. We have the full multiple polylogs. Now I'd like to introduce the symbol, which is arguably the most spectacular application of the coproduct on Feynman integrals of serious physical interest. So we use the fact that the coproduct, or the coaction above, is graded. So we can define a specific component with respect to the grading. Say delta k comma n minus k is the map from the weight n multiple polylogs to the space of weight k tensor weight n minus k. So for example, delta k comma n minus k acting on Li n of z would be Li k of z tensor log to the n minus k of z over n minus k factorial if k is greater or equal to 1. And if k is 0, then it's 1 tensor Li n. And we can, as we iterate the coproduct, we can further define for any partition of n into integers, n equals n1 plus nr, non-negative integers, of course, delta n1 dot 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 nr is the map from the weight n polylogs to this space in which, after r minus 1 iterations of the coproduct, we arrive at the decomposition into precisely this set of weights. Recall that the coproduct is co-associative, so this is well defined. It doesn't matter in which order you iterate the coproduct. Now, having defined this, let's consider the maximal iteration to the partition into ones, n of them. So this is a map from weight n polylogs to weight 1 tensor, well, really broken down into weight 1 components. And weight 1 MPLs are logs, or perhaps logs evaluated at specific values. So this is one construction of the symbol map. And since everything there is some kind of log, whether the argument is a variable or a number, we'll just drop the log, writing log, by convention. So for example, the symbol of log x, it is log x, but since by convention the way we notate symbols is to drop the log, we write that it's x. The symbol of log to the n of x is n factorial times x tensor x tensor x taken n times. The symbol of log x times log y would be x tensor y plus y tensor x. Recall this is easier to see from our formulas from before. We had here, right, this is the full coaction. So now when we have this, we're just selecting the terms that have weight 1 on each side of the tensor product and dropping the logs, and that's precisely this. We have the symbol of ln of x would be minus 1 minus x tensor x, and the rest are all x. So we have n minus 1 times the x appears here. And when we're working with symbols, it can be slightly tricky to remember that really there is an implicit log everywhere. So if you have a factor, a rational number factor out front that is not equivalent, where you can't just scalar multiply this by x. This is really sort of separated from the symbol part that's written. And log identities apply, since these are all arguments of logs. So when we write symbols, we would have, for example, a tensor b plus a tensor c is a tensor, the product bc. And if we have, say, 1 over a in the middle of some symbol, that would be minus 1 times the same symbol where 1 over a is replaced by a. If we have 1 in the middle of the symbol, well, that's really log of 1, which is 0, so the whole thing is 0. And these symbols can be used to check identities or even to produce identities involving polylogarithms. And one example is the famous 5-term identity for the dilogarithm. So let's just look at this more closely to get a feeling for how symbols work. Here's one way to write this identity. So Li2 of x over 1 minus y plus Li2 of y over 1 minus x minus Li2 of xy over 1 minus x 1 minus y equals Li2 of x plus Li2 of y plus log 1 minus x log 1 minus y. Now, notice I've called it a 5-term identity, and I've written 6 terms. It is actually known by the 5-term as the 5-term identity, and it has a few different presentations in the literature. And if you define the dilogarithm slightly differently, you will actually get exactly 5 terms. But notice, I mean, we still have 5 terms that are the dilogarithm, and then let's say we have this extra term. That's log times log. So let's just write out the symbol of the left-hand side. So using this formula we have here for Ln, for the symbol, we start writing 1 minus, and then 1 minus that, which is 1 minus y minus x over 1 minus y, tensor x over 1 minus y, minus, and then 1 minus the next argument, which is 1 minus x minus y over 1 minus x, tensor y over 1 minus x, plus now 1 minus this argument, which is 1 minus, multiplying out the denominator, right, we get 1 minus y minus x minus xy, but then that's the part that's added back in over this product of factors in the denominator, tensor xy over 1 minus x, 1 minus y. And if we simplify this a little bit, let's collect the terms with 1 minus x minus y in the first entry of the symbol. So doing that with this minus sign, right, we can invert this factor. So we'll get 1 minus y over x. Same thing for the second term. And remember, by log identities, if we have a common argument here and we're combining these two terms, we combine that as the product and the argument of the logarithm. And then we have, apart from the last term as well, and that's xy over 1 minus x, 1 minus y. Okay, then the next factor we would have is 1 minus y in the first entry, 1 minus y, and collecting everything there. So this appears here and also here. So we get two factors, x over 1 minus y, 1 minus x, 1 minus y over xy, accounting for signs, and then finally plus 1 minus, sort of the same thing except with x and y exchanged. So that would be y over 1 minus x, 1 minus x, 1 minus y over xy. Now notice here, right, everything cancels and we're left with 1, and when you have 1 in the symbol, then that term in the symbol goes to 0 identically. Here we have a bit of cancellation and there's something left. Same here. And you can check that this reproduces exactly what you get from the symbol on the right-hand side. So I'll leave that last little bit as an exercise. Now the symbol gives us a lot of information about the original function, and it seems, of course, when we take a symbol, we are losing some information in principle because we're only taking one component of the coproduct. And then, of course, the coproduct itself loses, or to really say coaction, loses some information in particular because the second entry can only be evaluated modulo I pi. So a remarkable feature of a property of the symbol is that, in fact, it does contain nearly enough information. There is the Durgangle-Rhodes algorithm by which you can reconstruct a given function knowing just its symbol, and then further reconstruct with a small amount of numerical matching the bit of information that you might have lost along the way. Let me just mention there is a condition for a symbol. If you just write down some symbol, of course it's not guaranteed it would be the symbol of some function. So a necessary and sufficient condition for a symbol to belong to some function is called integrability. This condition is that if you have a symbol, which we can express as some, in terms of its coefficients, times its arguments, xi1 tensor xi2 up to xin, that this is a symbol of some function if and only if this condition holds, that we take the same coefficients, and for each term we just select consecutive pairs, and we're constructing a differential. So d log xik wedge d log xik plus 1. This times the rest of the symbol. So now we're going from ik minus 1, two of them have been removed, to ik plus 2. Up to in. This should be 0 for all values of k, so really for any consecutive positions in the symbol. I'd like to mention an alternative definition of symbol. In fact, the original one. It was defined recursively in terms of differentials for transcendental functions, constructed from iterated d log integrands. So if you have a function f of transcendental weight w, and you have the differential, which is then a sum of functions of whose transcendental weight is 1 less times d log of some argument, then you construct the symbol recursively in terms of the symbols of these lower weight functions. Symbol of all these fi, weight w minus 1, by putting tensor ri at the end of the symbol. So if you apply this to MPLs defined from the i's, and again with generic arguments so we don't get into trouble, that would give you that di of a0 through an plus 1 is the sum from 1 to n, where we omit one of the middle arguments. So we omit each of the middle arguments in turn. ai minus 1 goes to ai plus 1, an plus 1, and then this times d log ai plus 1 minus ai over ai minus 1 minus ai. So then it's this combination that is appearing in the symbol iteratively for each term. So just in closing now, I want to point out an important property of the coaction, which makes it very useful for physical applications, and that it interacts very nicely with discontinuity operations and differential operators. So the coproduct of a differential, just a derivative with respect to any of the arguments of the function, is the identity times that same differential acting on the second entry of the coproduct. And the discontinuity, any kind of discontinuity or monodromy operator, is sort of complementary. It acts only in the first element of the coproduct, if you take the coproduct on both sides. So this has been proved for generic arguments, and again for non-generic arguments you have to be more careful, but in many cases it continues to hold. And this will turn out to be useful when we apply these operations to multiple polylogs that appear in Feynman integrals or the Feynman integrals themselves.